The tandem queuing network is the special case of open queuing network, in which all the nodes or the queues are interconnected in a series. Let me start with the very simplest tandem queuing networks with two nodes or two queuing system connected in series. We are going to relate the queuing network with the stochastic process and so on. Therefore, let me start with the random variable x of t and y of t. X of t denotes number of jobs or customers in the node 1 at any time t. Node 1 or first queue, both are one and the same. Yt, the another random variable, that denotes the number of jobs in the second queue at time t. Therefore, the together x of t and y of t, you can think of a vector as z of t is equal to x of t to y of t. That vector is a random vector at any time t, and if you collect over the t, then that is going to be a stochastic process. So, this stochastic process, instead of one random variable, it has a two random variables x of t and y of t, therefore, it is a vector. So, that is a stochastic process x of t comma y of t for t greater than or equal to 0, that is a stochastic process. Since x of t and y of t are the number of jobs in the first queue and second queue, and you are observing over the time how many customers in the first node and how many customers in the second node at any time t. Therefore, this is the discrete state continuous time stochastic process. Also, you assume that infinite capacity in both the nodes, both the queues. That means after the service is over in the first node, it will be immediately arrived into the second node, and if no customer in the system at the time, then he will get the service immediately, the service will be started immediately. Otherwise, the customer who comes after completing the service in the first node, he has to wait till his service started. So, I am making one by one assumption, so that the underlying stochastic process is going to be a continuous time Markov chain. That is my objective. So, for that, now I am making an assumption. The first assumption, the inter-arrival time of a customers entering into the first node, that is exponentially distributed with the parameter lambda, or the arrival process into the first queue is a Poisson process with the parameter lambda. So, the population is infinite, the customers are jobs or packets, for example, packets for the telecommunication system or any communication system. So, the customers are entering into the node 1, that process is a Poisson process with the parameter lambda. Now, I am making the assumption for service, I make the assumption for the service time, that is also exponentially distribution with the parameter mu 1 for the first node and mu 2 for the second node. Other than the inter-arrivals are exponential distribution, I made the other assumptions, that is the service time for the first node and the service time for the second node, both are exponentially distributed with the parameters mu 1 and mu 2 respectively. So, ultimately I want this has to behave as a MM1 queue, and this also has to behave as a MM1 queue independently. Therefore, I make all the assumptions, the inter-arrival times are independent with the service for the first node. Similarly, this one is the arrival for the second node is independent of the service of the second node, and so on. So, with that assumption, each queue in this queuing network is going to behave as a MM1 queue, and the departure of the first node, that is will be the input for the second node. And here you can use the Buck's theorem This is a M1Q model. Therefore, using the Buck's theorem, you can conclude the departure process is also Poisson process, because the arrival process is a Poisson and the service rate is mu1. Using the Buck's theorem, you can conclude the departure process is also Poisson process with the parameter of the same parameter of arrival process. Therefore, here the arrival process for the node 2 is also Poisson process with the same parameter lambda. It is independent of the service. Not only that, the departure process is independent of the number of customers in the system and so on, and the inter-arrival. Therefore, you will have a two independent M1Q using the Buck's theorem. Now, this will separately act as a M1Q because the arrival process is a Poisson with the parameter lambda, and already we made the assumptions arrivals are independent with the service. Service is exponentially distributed with the parameter mu2. After the service is over, the customers leave the system. Therefore, this is a separate M1Q because we made an infinite capacity in both the queues. Therefore, the two queues tandem queue, the underlying stochastic process x of t comma y of t going to be the continuous time Markov chain, So, now I am going to formulate the CTMC from the two queues tandem queuing network. The transitions due to arrival or departure of jobs in each queue. Based on this, I can make a state of the system x of t comma y of t, and that is going to be a continuous time Markov chain. This is not going to be a birth death process because you have a two random variable x of t and y of t, and each one independently a M1Q. M1Q is the underlying stochastic process for the M1Q, that is a birth death process, whereas here you have a together x of t comma y of t. Therefore, this is not going to be a birth death process, it will be a general continuous time Markov chain. So, once we identify this as a continuous time Markov chain, because the Markov property is satisfied by the stochastic process x of t comma y of t, I can go for drawing the state transition diagram. It is Markov in nature because the two queues act independently and are themselves a M1 queuing system which satisfies the Markov property. The first index is for the number of customers in the first node, and second index is for the number of customers in the second node. So, 0, 0 means in both the queues no one in the system. If one arrival comes into the first node, arrival cannot come into the second node, only the arrival come to the first node, the inter-arrival is exponential distribution. Therefore, the rate of moving from 0, 0 to 1, 0, that is lambda. Similarly, there is a possibility of one more customer entering into the system when one customer in the first queue. So, it will be a parameter lambda. Therefore, the rate will be lambda for the aux moving from 0, 0 to 1, 0, 1, 0 to 2, 0 and so on. Whereas, after one customer already in the first node, the server in the first node who would have completed the service before the one more arrival into the first node. Therefore, the service is exponential distribution with the parameter mu1. Therefore, the system goes from 1, 0 to 0, 1. That means the customer who was under the service, that service is over. Therefore, he moved into the second queue. Now, the first node has a 0 customer and the second node has 1 customer in the system, and his service will start once he enter into the second node. So this rate will be mu 1. Now the situations are either one arrival to the first node, or the customer who is in the second node, he would have completed his service. So that service is over, therefore that rate is mu 2. Then the system goes to 0, 0, or it will go to 1, 1 with the rate lambda. So the same way one can discuss for 1, 1 also. That means one customer in the first node, one customer in the second node. So the one possibility is the first customer's service is over, therefore it will be 0, 2 with the rate mu 1, or one more arrival takes place, therefore it will be 2, 1 with the rate lambda, or the second service would have been finished. So that rate is mu 2, therefore it is 1, 1 to 1, 0. So these are all the possibilities. The system can move from 1, 1 to other states 0, 2, 1, 2 or 1, 0, and so on. So this is the way you can visualize the different transition arcs and the corresponding rates. So this is a state transition diagram for a 2 queues tandem queuing network. Obviously from this diagram itself you can say that this is not a birth death process. If it is a birth death process and the system has to move forward one step or backward one step, no other moves. So here you have a 2-dimensional Markov chain, therefore this is not a birth death process, it is a continuous time Markov chain.